from University of Louisville. Today, I, Dr. Ghassanifar, and Amin Mohamadzadeh and Mertad Najafian, we're going to show you the importance of matrix suction and its effect on the effective stress and measurements in the lab. Effective stress, normally when we consider effective stress in saturated condition, we consider it only the total stress minus water pressure, poor water pressure. But in unsaturated soil, we do need to consider the matrix suction, that matrix suction will increase the effective stress. So in general, effective stress is the total stress minus air pressure plus Bishop's coefficient times the matrix suction. To get the matrix suction, we have different sensors, and different type of soils have different ranges of matrix suction. As you can see, that's how we can relate it to the soil water characteristics curve that shows the variation in matrix suctions versus the degree of saturation or water content. We have different type of soil here. The pink one shows sandy soil, blue is silt, clay loam, and the orange one is clay. As you can see, the range for the matrix suctions is different. Sandy soil usually shows a kilopascal, a range of kilopascal to a max of 100 kilopascal of the matrix suction. Wire, silt, and some clays can be up to megapascal, and even clay can show a gigapascal matrix suctions. And to relate this behavior and to use it for the design, soil water characteristics curves help us to relate suction for different moisture content. So we here in this blackboard, we showed the equation of Van Gunutian, one of the traditional equation to relate the matrix suction and moisture content, which relates to the saturated water content and residual water content. The residual water content towards the dry side and the saturated water content, and alpha, which is the related to the air entry value, and n, which is a fitting parameter, which relates to the soil size, pore size distribution of the soils and soil parameter. So today I am going to work with Mertad and Amin to show you how we do measure this for sandy soil and clays.
So as Dr. Ghassanifar explained, to get the RC curve, we need to measure suction at different water content. So for that, we prepared a sample of sandy soil, and we added the water to the soil and compacted to our desired density in the cylinder. So we need to know the amount of water content and suction at this level. For that, we're using a sensor which measures the moisture content, and also we're using another sensor which gives us the matrix suction at this water content. So by inserting these sensors inside the soil sample and connected these sensors to the data logger and to the computer, we can read the matrix suction and moisture content at this level. So we repeat this process for different water contents, so we can get suction at different water contents, and finally we can come up with the whole SWRC curve.
So for the sandy soil, we're using Terrace 31. It's a very sensitive sensor because we are working with the low range of suction. And moisture content 5 TM we are using is a specific sensor that measures both temperature and moisture. But for this experiment, we only need moisture so that we have a moisture content and we can get the matrix suctions. And these samples we need to be calibrated and be ready for the test.
So another sample that we have is a clay sample. For measuring the suction in clay sample, we need to use the Terrace 21, which first it needs to be coated with a very moist clay, then inserted in the sample, and then read it from the computer. And afterward, we can take a sample and put it in an oven to be oven dry for 24 hours and calculate the water content.
Since sand and clay have different matrix suction ranges, we do use different sensors for measuring the matrix suctions. Then we can get each points, and then we can get soil water characteristics curve, or SWCC, or the name also is a soil water retention curve. Thank you for watching us.